Today we're going to be starting chapter 12, and there's 3 ideas that we're going to be learning about in chapter 12. All of them are dealing with counting. The first one is going to be the fundamental counting principle that we're going to be covering today. So if you want to get out your composition book, we're going to add some notes in, and also get out the worksheet that I sent you guys on Google Classroom, 12-1 to 12-6. So on our table of contents, we're going to title this Chapter 12, Counting and Closure. And the first topic we're going to be doing is the fundamental counting principle. So I'm going to be turning to a fresh page to start our notes on fundamental counting principle. So fundamental counting principle. And the fundamental counting principle states the following. If one event occurs m ways, and another event occurs n ways, then together the two events can occur m times n ways. Then together the events can occur m times n ways. Now, I'm also going to put a little note here. This is assuming that the second event is not influenced by the first event. So assuming that the second event is not influenced by the first event. So if the second event is changed by the first event, then this may not be n anymore. It might be something less. And we'll see that in some of our examples. So our first example, let's say you have 10 shirts, seven pants, and 2 jackets. And you want to figure out how many different outfits you can make. So how many different outfits can you make? And we're going to assume that either everything matches or you don't care. So we're going to make something called a decision chart. And then we're going to use the fundamental counting principle idea. So we have 3 different decisions that we need to make. We need to make a decision on shirt, on pants, and on jacket. So I'm going to have shirts, jackets, and pants. Those are the 3 things we're debating about. So I'm going to look at the shirts. We have 10 shirts. So we have 10 choices for our shirts. For the jackets, we have 2 jackets, so I have 2 choices for my jackets. And for my pants, we have 7 pants, so we have 7 choices for our pants. And we're going to multiply 10 times 2 times 7, following the fundamental counting principle, and we're going to get 140 different outfits. So now we're going to switch over to the worksheet, and we're going to use this information to help us with some of the problems. So I'm going to show you the worksheet on my phone, just to show you guys that you guys can edit it using the Google Classroom if you have the app on your phone. So I'm going to go to the worksheet for today, 12:1 to 12:6. And I'm going to come down here, and there's the PDF for me. Oops. And you see the little pencil here at the top that allows you to edit. So I'm going to click on that. I'm just going to turn my phone sideways so we can see it a little better. And we'll go through the first question on my phone, and then we'll do the rest on the worksheet. So I'm going to use a stylus to write, but you can also just use your finger. It will also work. So on this problem, we're going to use the idea of the fundamental counting principle. So 12:1. Nick's new phone is prompting him to choose a 4-digit passcode. On the screen, it says choose any digit 1 through 7. After typing in that first digit, the flashing dash prompts him for the second. As he thinks about his second choice, he wonders how many different passcodes are possible. So he says, I need a decision chart. He writes the following diagram on his paper. So he has for his first, for his second, and for his third and fourth digit. So again, we have the numbers 1 through 7 that we can pick. So for the first digit, he has 7 options. Now it does not say that it cannot repeat, so we are going to assume that he can use all 7 again. And then again for the third one and for the fourth one. So in this case, since it did not say it cannot repeat, we could have 7 choices for each of the 4 digits. And that ends up being 7 to the 4th. And if I put that in my calculator, I get 2,401 as my answer. So now, let me move to the next problem. So here, again, this was actually the same question. They wanted us to fill out the decision chart, and they wanted us to figure out how many. So that's my answer, 2,401. On part B, it says, what is the probability that Nick's randomly selected 4-digit passcode will be 2,763? So remember, he had 2,401 total possible passcodes. This 2,763 would be 1 out of that. So our answer is going to be 1 out of 2,401, and that's going to be our answer. Now, just a quick note before I go back to the actual worksheet. Up here, if you click these 3 little dots, you see save. So you can save that and come back and edit it later. If you don't hit save, it's not going to keep it on the document. It's just going to keep it as it was blank. So I just want to make sure everyone understands that. So now I'm going to switch to the worksheet. And we're going to be looking at 12-2. And again, you guys can be doing this on your phone if you want, or you can do it on the paper if you prefer. How many different 4-digit numbers, passcodes, could you make using the digits 1 through 7 if you cannot use any digit more than once? So again, we still are using the digits 1 through 7. We have a 4-digit passcode, but the difference here is that you cannot use any digit more than once. So once we've used it, it's gone. So I'm going to make my decision chart. And so for my decision chart, I'm going to have my first, second, third, fourth digit. Now for the first one, I'm going to have 7 choices because all 1 through 7 will be available. But once I've used that first number up, I no longer have it to use. So now I'm going to have 1 less. I only have 6 numbers. And now that I've used 2 numbers, I now again have less. I have only 5 numbers left. And then 4. So now we're going to work that out. So we're going to take 7 times 6 times 5 times 4. And we end up with 840. And that is our answer. So now on the second one, or on this next one, 12-3, you guys are going to use a decision chart to answer each of the questions below. So I'm going to read through this, and then you guys are going to have some questions to answer and see if you guys can get these right. So a game contains 9 discs, each with one of the numbers 1, 2, 3, 4, 5, 6, 7, 8, or 9 on it. How many different 3-digit numbers can be formed by using any 3 discs? So just so you understand, in this situation, we have the following. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 discs, and each disc has a different number on it, 1 through 9. So right now, set up a decision chart and figure out how many different possible numbers can be formed, 3-digit numbers, using this system. So for this, I am going to have 3 slots for my decision chart. The first disc, the second disc, the third disc. Now, for the first one, I have 9 choices, 1 through 9. But now for the second one, I've already picked one of those discs, so I don't have all 9 anymore. I now have 8. And then the next time I have 7. So I'm going to be multiplying this out. So I'm going to take 9 times 8 times 7, and I end up with 504 different 3-digit numbers using this method. So now let's take a look at part B. So for part B, a new lotto game called Quick Spin has 3 wheels, each with the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9 equally spaced around the rim. Each wheel is spun once, and the numbers the arrows point to are recorded in order. How many different 3-digit numbers are possible? So in this situation, we're going to have one spinner, and on that spinner, we're going to have the numbers 1 through 9 equally spaced on this. And we have a second spinner that again has the numbers 1 through 9 equally spaced. And then we have a third wheel with the numbers 1 through 9 also equally spaced. So for this one, you're going to set up a decision chart and come up with the answer to how many different 3-digit numbers are possible in this situation. So for this problem, I am again going to have, just like above, 3 slots. One's for my first digit, one for my second digit, and one for my third digit. Now, both cases we have the numbers 1 through 9. In this case, each spinner has the numbers 1 through 9. So for the first spinner, I'm going to have 9 different outcomes possible. And then when we go and do the second spinner, it also is going to have 9 different outcomes possible. And when we spin the third spinner, it's also going to have 9 different outcomes possible. So this is 9 times 9 times 9. or 9 to the third, and 9 to the third is 729. So we have 729 possible choices. So now on part C, it says, explain the similarities and differences between part A and B. So some of the similarities, both of them are 3-digit numbers. So both are 3-digit numbers. Both of them also are using the same digits 1 through 9. But you see that we did get 2 different answers here. In the first one, we could not use repetition. Once a number was used, we could not use it any longer. In the second one, we could use that same number over and over again. So we had repetition. So in part A, we could not repeat a number. While in part B, we could. So now let's look at the next problem, 12-4. Marcos is selecting classes for next year. He plans to take English, physics, government, pre-calculus, Spanish, and journalism. His school has a 6-period day, so he will have one of these classes each period. How many different schedules are possible? So right now, set up a decision chart and figure out how many possible solutions. So in this case, we'll have period 1, period 2, period 3, period 4, period 5, period 6. He has 6 choices for period 1. Now, once that class is selected for period 1, he's not going to take it again during the day. So now he only has 5 choices for period 2, 4 choices for period 3, then 3, then 2, then 1. So when we put that in our calculator, 6 times 5 times 4 times 3 times 2 times 1, we end up with 720 different class schedules that he can have. So now, in the next one, it says, how many schedules are possible if pre-calculus is first period? So in this case, I'm going to set it up like I did above. So again, I've got my 6 periods. Now, how many schedules are possible if pre-calc is period 1? So we know that pre-calc is period 1. So in this case, we know he's going to have one way for that to happen. There's only one way to get pre-calc period 1. So now this one class has been used. So he no longer has 6 classes to pick from. So the next period he has 5, and then 4, and then 3, and then 2, and then 1. So now we are going to multiply this out. So 1 times 5 times 6, 1 times 5 times 4 times 3 times 2 times 1, we end up with 120. So if he needs to have pre-calc period 1, that shrunk down how many different schedules he could have. Now he only has 120. So now on C, we're going to be dealing with a probability question. It says, what is the probability that Marcos will get first period pre-calc? Why? So we know that he has 120 ways to get pre-calc out of 720 total schedules. So we are going to take the 120 ways that he can have pre-calc first period out of all total schedules, which is 720. And we're going to work that out. So 120 over 720 ends up being 1/6, or as a decimal, it's 0.16 repeating, so 16.6%. So then it ends up being 1/6 or 16.6%. So now the next problem, problem D, what is the probability that Marcos will get both first period pre-calc and second period physics? So I'd like for you guys to figure this one out. Again, remember, it is a probability. So if I am doing a decision chart for this, again, we have period 1, 2, 3, 4, 5, 6. Now, in order to get his pre-calc first period, there's only one way that that can happen. In order to get his second period physics, there's only going to be one way that can happen. So now we have 2 classes already selected out of the 6. So for period 3, we're only going to have 4, then 3, then 2, then 1. And when I work this out, this is going to end up being 24. So that 24 is all of the ways he can get the schedule. So we're going to have that 24 out of our total schedules, which was up here, 720. And when I put that in the calculator, (24 over 720) ends up being 1/30, or 3.3%. So again, that ends up being 1/30, or 3.3 repeating percent. So now, the next problem, we're going to be learning about a new function. And that function is this n factorial. Okay, this exclamation point means factorial. So exclamation point means factorial. Okay, and it is an operation that we're going to be seeing here. Now, if you have a graphing calculator, on the graphing calculator, there's 2 different places that you can get to this. One of them is going to math. And then when you go to math, it's under probability. To get there, you can either arrow to the right. I like to arrow to the left and go backwards. It's a little faster. And here, number 4 would be that. Another way to do it, and this is how I normally do it, is I will press alpha. Remember, alpha and y equal gives us all the fraction options. Alpha and window gives us different options. And the one we want is number 9. And that's where we would get our factorial. Okay, so let's say, for example, I want to go 10 factorial. So I would type in my 10, I go to alpha window, hit number 9, and it's going to give me the answer, 3,628,800. So right now, look for it on your phone, or you can also use Desmos. And let me show you how to do that. So on Desmos, let me share my screen. So if you're doing this on Desmos, just this out of the way. We're just going to go to start graphing. And if I want to do 10 factorial, all I need to do is 10 and the exclamation point, and it will do 10 factorial for me. So you can also use Desmos for this. So again, on Desmos, just put in the number you want to take the factorial of, and then use the exclamation point. So right now, what I'd like for you guys to do is try to figure out the number one, where that is on your calculator, and then work out all of these. And then we'll talk about it when I get back. So this is what I ended up with. 40,320, 5,040, 720, 120, 24, 6, 2, and 1. Now for part B, it says, which result is the same as the number of Marcos's possible schedules? So remember up here, his total schedules, he had 720. 720 possible schedules. And we worked that out by doing 6 times 5 times 4 times 3 times 2 times 1. So the one that it matches up with is this 720, which is 6 factorial. Now, it asks us in the next question, what do you think 6 factorial means? Well, since 6 factorial gave us the same answer as 6 times 5 times 4 times 3 times 2 times 1, that's what 6 factorial equals. 6 times 5 times 4 times 3 times 2 times 1. So on part D here, it says, explain why 4 factorial gives the correct solution to the possible number of ways to arrange the letters M, A, T, H. So we have these 4 letters, and we're going to put them in different orders, and we want to know how many. So first, second, third, fourth. So for the first one, we have 4 different letters we could pick from. And then once I pick that letter, I now only have 3 left, then 2 left, then 1 left. And 4 times 3 times 2 times 1 is 4 factorial, which is 24. So now what I'm going to do is I'm going to switch over to notes, and we're going to add in factorials into our notes. So now let's go back to our notes, and we're going to add in a new section. And this is going to be titled Factorials. And factorials, if we have n with the exclamation point, again, it's read n factorial, that is equal to n times the number in front of n, which is n minus 1, and the number in front of that, which is n minus 2, and so on, all the way down to 3 times 2 times 1. That's what n factorial is. So for example, if I wanted to do 5 factorial, it would be the same as 5 times 4 times 3 times 2 times 1. That is the same as 5 factorial. So instead of typing out all of these in my calculator, I could just type 5 factorial. It's going to give me the same answer. Now, a little note, 0 factorial is equal to 1. So that's something that you guys want to know, that again, 0 factorial is equal to 1. So now I want to just add in 2 examples using the factorials with what we were doing earlier. So let's say, for example, there are 6 players on a volleyball team. So there are 6 players on a volleyball team. And we want to know how many different lineups can the coach come up with? How many different lineups can the coach make? So we can do this in a couple different ways. We can do our decision chart, first position, second, third, fourth, fifth, and sixth. So the first person, he has 6 choices for that first placement. Then once that person's used up, he only has 5, and then 4, and then 3, and then 2, and then 1, or 6 factorial. And when we put that in our calculator, 6 factorial is equal to 120. So 720 different lineups. Okay, 720 different lineups. Now I'm going to take this one step further. In this case, we had 6 people for 6 positions. What if we have more people than positions, which usually happens on a team? So next example, there are 11 players on a volleyball team. But only 6 positions on the court. So we want to know how many different lineups are possible. So for this, we can do it a couple different ways. I'm going to start with a decision chart. So again, we have 1, 2, 3, 4, 5, 6 positions, okay, on the court. We have 11 people to pick from. So for the first choice, we have 11 people we can pick for that position. Now, once that player's gone, and in that position, we only have 10, and then 9, and then 8, and then 7, and then 6. Now, you'll notice that this is not 11 factorial. We are missing, right here, we are missing 5, 4, 3, 2, 1 is missing, okay? So we can type all this in our calculator, 11 times 10 times 9 times 8 times 7 times 6, but notice that we are missing 5 factorial from 11 factorial. So another way to think about this, the same thing, you can type in 11 factorial over 5 factorial, because what we're doing is we're taking away the 5, 4, 3, 2, 1 that's missing. So let me show you on the calculator that both cases I end up getting the same answer. So again, 11 times 10 times 9 times 8 times 7 times 6. And I put it in as 11 factorial over 5 factorial, because 5 people are not going to be picked. So I don't care about the order of those 5 people. You end up with the same answer. So now let's switch back to our worksheet and continue with this idea. So now let's come back to 12-6. It says, remembering what n factorial means can help you do some messy calculations quickly, as well as help you do problems that might be too large for your calculator's memory. For instance, if you wanted to calculate 9 factorial over 6 factorial, you could use the factorial function on your calculator to calculate 9 factorial and get 362,880, and 6 factorial and get 720. So 9 factorial over 6 factorial is this. You can put that in your calculator and work it out. Or you could simply do the following. Since 9 factorial is 987654321, and 6 factorial is 654321, you can write it like this. Now, when we're writing it like this, what you'll notice is on top, I have a 654321 and another 654321. So those can cancel each other out. So all of these 654321 and 654321 will cancel out, and I'm left with 9 times 8 times 7, or 504. Now, when I do a problem like this, I'm going to do it over here. What I'm going to do is I'm going to take 9 factorial, and I'm going to break 9 factorial like they did, but I'm going to stop it at 6 factorial because this right here is just 6 factorial. I don't need to write it out. So I'm going to go 9 times 8 times 7 times 6 factorial. And again, this is 654,321 over 6 factorial. And now the 6 factorial on top and bottom cancel out. And now I'm just doing 9 times 8 times 7, which is 504. So what I'd like for you guys to do, I'd like for you guys to now do this type of an idea for each of these problems, breaking it down to the factorials like this, and then compute your final answer with what's left over. So try those now. So hopefully you got the following. I'm going to take this 10 and take 10 times 9 times, and I'm going to stop at 8 factorial because I have an 8 factorial on the bottom. And this 8 factorial on top and this 8 factorial on bottom are going to cancel. And now I am left with just 10 times 9, or 90, and that's my answer. Now, when you're doing the next one, I'm going to take 70 and I'm going to stop at 68 factorial. So I'm going to go 70 times 69 times 68 factorial over 68 factorial. And again, the 68 factorials are going to cancel out. And I'm going to be doing 70 times 69. So 70 times 69 is 4,830. So 4,830. Now, C and D are slightly different. What I'm going to do is I like to take this 7 down to the bigger of the two numbers. That way I have more cancel out. So I'm going to do 7 times 6 times 5 times 4 factorial over 4 factorial. And now the 3 factorial I'm going to write out as a 3 times 2 times 1. So this 4 factorial and this 4 factorial are going to cancel out. And now I can also take my 3 times 2 times 1, which is 6, and it can cancel out with the 6. So again, this 3 times 2 times 1 is going to cancel with the 6, and I am left with 7 times 5, or 35. Similar idea on letter D. Again, I'm going to take this 20 down to the bigger of the two factorials. So I'm going to go 20 times 19 times 18 factorial over 18 factorial times, and now my 2 I'm going to do is a 2 times 1. So I have my 18 factorial and 18 factorial canceling out. And then I'm going to have my 2 times 1, which is 2, can cancel with part of my 20, leaving me with a 10. So now I have 10 times 19, which is 190. So You can be using these ideas tonight when you do your homework, which is going to be a worksheet on the fundamental counting principle.